Greetings everyone, I am Rahul Singh and today I will be giving a seminar presentation on the topic Marine Concrete. Table of Contents. Introduction, Need for Marine Concrete, Composition of Marine Concrete, Difference between Standard Concrete and Marine Concrete, Advantages and Disadvantages, Case Studies, Conclusion and References. Introduction. Standard concrete is designed for environments that do not face aggressive conditions like seawater, freezing and thawing, or heavy chemical exposure. Marine concrete, on the other hand, is specifically designed to withstand the harsh conditions of marine environments, where it is exposed to seawater, salt like chlorides, abrasion from waves, ships and cargo handling, and chemical attacks from sulfates and other substances. It is used in marine structures like quays, docks, offshore platforms, piers, breakwaters, and jetty foundations. Marine concrete structures must be robust enough to withstand the harsh marine environment and the action of sea-going vessels. For larger structures like seawalls and breakwaters, this robustness is achieved through mass and bulk, whereas for smaller structures, this robustness is achieved by protecting them from excessive wave action and corrosion. Marine concrete structures are designed according to various standards. IS 3370 Code of Practice for Concrete Structures for the Storage of Liquids, Part 2, which covers reinforced concrete structures, and IS 456 2000. Need for marine concrete. The need for marine concrete arises from the unique challenges and demands of constructing and maintaining infrastructure in marine and coastal environments. Unlike standard concrete used in general construction, marine concrete is specifically engineered to withstand the harsh conditions of saltwater, extreme weather, wave action, and other environmental factors typical of coastal and underwater environments. As seen from Figure 1, marine structures are subjected to various hazardous environmental conditions that may compromise the performance and safety of the structure. Hence, marine concrete is used in the development of marine structures. Composition of marine concrete. Type of cement. Portland pozzolana cement or PPC. This cement is often preferred for marine applications due to its resistance to sulfate and chloride attack. Sulfate resistant cement or SRC. It is used when concrete is exposed to high sulfate environments such as seawater. It provides enhanced resistance to deterioration caused by sulfate salts. Aggregates. The coarse aggregates, for example, gravel or crushed stone used in marine concrete, are chosen for their strength, abrasion resistance, and low water absorption. Sometimes marine aggregates may also be used in some special cases, for example, crushed coral or granite, in order to meet specific performance needs. Reinforcement. Stainless steel rebar. In some highly corrosive environments, stainless steel rebar is used as it has a higher resistance to corrosion than regular carbon steel. Coated rebar. Rebars coated with an epoxy layer are used to protect the steel from chloride penetration, significantly reducing the risk of corrosion. In some advanced applications, non-metallic reinforcements such as fiberglass or carbon fiber can also be used in order to avoid corrosion. These materials have high strength and do not corrode, although they can be much more expensive. Water. The water used for mixing should have minimal chloride content to avoid further exposure to corrosion. Additives or admixtures. Corrosion inhibitors. Corrosion inhibitors can block chloride ions from reaching the steel bars and form protective layers around the steel. For example, benzotriazole, sodium nitrite, and calcium nitrite. Waterproofing admixtures. These are used to reduce the permeability of the concrete, making it less susceptible to water infiltration. For example, crystalline waterproofing agents, hydrophobic agents, and membrane waterproofing agents. Superplasticizers. These are high performance chemical admixtures that help to improve the workability of concrete without increasing the water content. Superplasticizers allow the concrete to be poured more easily and compacted more effectively, which is essential in marine conditions. For example, Mayplast SF from the company Mapei. Air entraining agents. These chemicals introduce small, stable air bubbles into the concrete mix, which improves the concrete's resistance to freeze thaw damage and increases its overall durability. For example, Air Plus from Mapei. Pozzolanic materials. Pozzolanic materials are used to enhance the durability of concrete by reacting with calcium hydroxide in the presence of water to form calcium silicate hydrate, which improves strength and reduces permeability. For example, fly ash, silica fume, and ground granulated blast furnace slag. Here are the differences between standard concrete and marine concrete. Property: environment. Standard construction, buildings and roads for standard concrete, and marine concrete is used for harsh marine environments, for example, ports. Exposure: standard concrete is minimally exposed to any seawater or chemicals, whereas marine concrete has constant exposure to seawater, salts, and abrasion. Composition: standard concrete consists of cement, water, sand, and gravel. Marine concrete, on the other hand, consists of cement, water, and special additives like fly ash, corrosion inhibitors, or waterproofing agents. Strength: the standard concrete has standard strength and range from M25 to M30, whereas marine concrete ranges from M40 to M70, which is high strength for durability. Corrosion resistance: standard concrete is prone to corrosion in seawater, whereas marine concrete has corrosion resistant materials and additives added in order to reduce corrosion. Applications: standard concrete is used for buildings, roads, bridges, and foundations, whereas marine concrete is used primarily for marine infrastructure, for example, quays, piers, or jetties. Maintenance: standard concrete requires periodic maintenance, whereas marine concrete can last long with low maintenance. Here are the advantages and disadvantages of marine concrete. The following are the advantages: longer lifespan. Marine concrete typically lasts longer than standard concrete, reducing maintenance costs. Marine concrete has high corrosion resistance, which protects the reinforcement from seawater induced corrosion. High strength. Marine concrete is suitable for demanding marine structures like offshore platforms. High durability. Resistant to seawater, chemical attacks, and corrosion. Resistance to freeze thaw, improve performance in freezing and thawing cycles. Disadvantages: higher cost. Marine concrete is more expensive due to the use of specialized materials and additives. Physical wear: it is susceptible to abrasion in high traffic marine areas. Slower curing. In cold or underwater conditions, marine concrete can take longer to cure. Environmental impact: production can contribute to high carbon emissions and environmental degradation. Difficult repair: repairing marine concrete structures can be challenging and expensive. Case study 1. This case study covers the construction of 4th Container Terminal FCT Phase 1 at Jawaharlal Nehru Port. Project overview. Location: Navi Mumbai area of Maharashtra, India. Project: construction of 4th Container Terminal FCT Phase 1. Developer: Bharat Mumbai Container Terminals Private Limited, which is a subsidiary of PSA International. Port Authority: Jawaharlal Nehru Port Trust Board, which oversees the operations and development of the port. Investments: approximately 4,719 crore INR. Operational timeline: construction began in 2015 and concluded in February 2018. Capacity: designed to handle 2.4 million TEUs, which stands for 20-foot equivalent units, annually. Quay length: 1 kilometer quay wall capable of berthing 2 ULCVs, ultra large container vessels, simultaneously. Water depth: a navigational depth of 16.5 meters, accommodating vessels with a capacity of 18,000 TEUs or more. Terminal area: 90 hectares of terminal yard with container stacking capacity. Here are the marine concrete specifications. Cement used: for quay walls and loading platforms, M50 PPC blended with ground granulated blast furnace slag for high durability and strength. Container yards: M40 PPC with additives to enhance abrasion resistance and reduce cracking. Piles and pile caps: M60 sulfate resisting Portland cement. For liquid cargo berths, M50 sulfate resisting Portland cement was used. Steel reinforcements: stainless steel bars and epoxy coated reinforcements with epoxy coating of thickness of 100 to 150 microns. Admixture use: silica fume was added to improve durability and reduce permeability. Corrosion inhibitors: calcium nitride based inhibitors were used. Concrete cover. Increased cover depth of 75 to 100 mm was specified to provide an additional layer of protection for reinforcements. Construction details. Foundation design. The quay wall and terminal foundations were constructed using board cast inside two piles. Pile diameter ranged from 1.2 to 1.5 meters, with depths reaching up to 40 meters below ground level, depending on the soil profile. Quay wall, 1 kilometer in length. A combination of cast in place concrete, precast concrete blocks were used in its construction. Water curing was used to prevent drying shrinkage and achieve full hydration of the cement. Aggregates were sourced from non reactive high quality quarries to prevent alkali silica reactions. Benefits of marine concrete in construction of fourth container terminal or FCT. Ensures structural integrity and safety in a highly corrosive environment, minimizes maintenance costs over the long term, enhances the port's operational efficiency by ensuring robust and durable infrastructure. Durable construction materials reduce the risk of structural failure and pollution from debris. Marine concrete was used to create effective drainage system preventing flood in the terminal area. Case study 2. This case study covers the use of marine concrete in Aberdeen Harbour expansion. The overview. The Aberdeen Harbour expansion project is a significant development aimed at transforming Aberdeen Harbour into a state of the art facility capable of accommodating large vessels and supporting diverse industries. The project focuses on expanding port capacity and enhancing its role as a key hub for offshore energy, fishing, tourism, and trade. Location: Nig Bay, south of existing Aberdeen Harbour, Scotland. Investment approximately £350 million. Timeline: construction commenced in 2017, completion operational start in 2022. Developer: Aberdeen Harbour Board. Marine concrete specifications. The cement used was as follows: quays walls M40 PPC was used, breakwaters M60 sulfate resisting Portland cement or SRPC was used, piles and foundations M60 sulfate resisting Portland cement was used. Admixtures: silica fume was added to improve durability and reduce permeability. Air and draining agents. Sulfonated lignin was used to improve freeze thaw durability in the cold Scottish climate. Steel reinforcements. Epoxy coated reinforcements were used to prevent corrosion due to saline water. Cathodic protection. Sacrificial anodes embedded in critical areas to mitigate steel corrosion. Construction details. Breakwaters. Length: two breakwaters totaling 600 meter were constructed using precast concrete caissons and armoring units to ensure stability and wave resistance. Rock sizes range from 1 to 10 tons were placed on the exterior of the breakwaters to absorb wave energy. Quayside. The quayside was formed with 22 precast concrete caissons with specifications: length 50 meter, width 12 meter to 14 meter, height 15 meter high, weight 8,000 tons. Foundation. Piles of diameter 1.2 to 1.5 meter and 35-meter depth were used for the foundation. Here is the pictorial representation of the Aberdeen Harbour expansion project. Conclusion: the use of marine concrete has been integral to the development of durable and cost effective infrastructure that can withstand the harsh marine environment. By addressing challenges such as corrosion, abrasion, chemical attacks, freeze thaw cycles, and environmental sustainability, marine structures have successfully ensured their long term performance and resilience. Here are the references. Thank you for your time.